Okay, we only have school through Wednesday this week. I gave weekly assignment 2 is posted. It's due the Monday after we get back from the long weekend. So I'm sure you'd have time to finish it this week if you want to. Um, so, anyways, uh, we're talking about centroids right now. I haven't given an assignment in a while, maybe. So let's just keep going with that and get far enough that you can do some problems. So remember, I said this last time. Um, there are 3 reasons that we're not going to have to use the integral definition. 3 reasons we won't use the integral definition of centroids. The first one is once someone uses that integral definition, once for a shape, it gives us an algebraic formula for that shape. So as long as somebody's ever done the shape that you're trying to do and you have the ability to find it, you can just use the algebraic formula. And last time, I think at the end of class, I gave you the list of the 3 or 4 shapes that we're going to use. There was a right triangle, a quarter circle, and a half of a parabola. And then also remember, even before we even talked about it as centroids, we always did circular shapes and rectangular shapes. And that's because the centroid of those is just right in the middle where you would think it would be. So we talked about those algebraic formulas. The second reason is the relationship. Well, let me word this differently. The centroid always lies on any lines or planes of symmetry you can find. By lines of symmetry, we're thinking of 2D shapes, and planes, we're thinking of 3D. But so now it makes sense thinking about it this way, why the centroid of say a rectangle is right in the middle. Well, if you use a vertical line to find a line of symmetry and then a horizontal line to find another line of symmetry, the centroid has to lie on both of those. So it has to lie at the intersection of those 2 lines of symmetry. And then the last thing is a sum formula, so that if we can build up a complicated shape out of simple shapes, we can use that. So I won't say anything other than that right now. But so let me start by talking about lines and planes of symmetry. In 2D, a centroid always lies on any line of symmetry. So if you can find two lines of symmetry, the centroid lies at their intersection. So for example, a rectangle, this is a line of symmetry, and this is a line of symmetry, and so the centroid has to be at their intersection. That symbol there that looks a little bit like a nuclear symbol with the circle with the diagonal dark corners like that is the sign for center of mass. And so I don't know, I haven't seen a commercial like this for a while, but it used to be car commercials always had crash test dummies in their commercials to show how much testing they did for safety. And the crash test dummies have this symbol all over them. And the reason for that is the center of mass is a really important location for doing physics. And so if you're watching like a high-speed video of a crash and you can track the location of the center of mass of their head and their upper arm and their lower arm and their torso and stuff, then you can use that video to go back and do all the physics and calculate the forces that they're feeling and stuff. So, yeah. Then another example is a circle. Well, this one has infinitely many lines of symmetry. There's one, there's one, there's one. But the key thing is that they all pass through the center of the circle. Oh God, that's a horrible drawing, but I'm going to fix it. Yeah. And so where they intersect is the centroid of the circle. In 2D, it works with planes of symmetry. It's harder to, in 3D, I mean. So in 3D, the centroid lies on any plane of symmetry. And if you can find three planes of symmetry, then the centroid is at the point where those three intersect. So if you have a shape like this, there is a plane of symmetry here. There's a plane of symmetry here. And then there's one here. And those three planes intersect at a point, and that point is right at the center of the rectangle, and so that's the centroid. One example, think of the quarter circle. Um, so this was one of the simple shapes that I gave you formulas for. And we were given that I called this X bar, and that was equal to 4r over 3 pi. Is that right? 4r over 3 pi, yeah. And then if we call this y bar, what's y bar equal to? Well, you can see that this is a line of symmetry. Okay, that's the line y equals x. And so y bar also has, if you know that x bar, you know y bar has to equal that. So it's also 4r over 3 pi. Okay, so those thinking in terms of symmetry can a lot of times cut down the amount of work you have to do, if even if it doesn't give you the total point. Like think of a shape of like a capital T, okay? Like if you don't notice that there's a vertical line of symmetry, then you have to calculate, use formulas and stuff to calculate the x and y components of the centroid. But if you notice that there's a vertical line of symmetry, then you don't have to worry about the x location. You already know what that is, and you can just spend your time, calculating the y location. Okay, so that is lines of symmetry, and that's always something to keep in mind. And then the third thing is the sum formulas. And this allows you to build up complicated shapes from simple shapes. Um, and so say that you have a body that can be decomposed into n shapes. So like, for example, this shape here, there's a few ways you could break it up, but we can break it up into a rectangle like that, a rectangle like that, a rectangle like that, and a semicircle. Or a semicircle is 2 quarter circles, so you could use the quarter circle idea, Then the centroid of the total shape, I'll do it 2D first. We're going to do 2D a lot more than we're going to use 3D. X bar, Y bar is equal to 1 over the total area times the sum from I equals 1 to n of xi, yi times the area of the ith shape. And this is the coordinates of the centroid of the ith simple shape. Notice that this is just a discrete version of the integral definition. So if you can remember this, you can remember the integral definition and vice versa. The integral definition said 1 over the total area times the integral of x, y, dA. That's just like this formula, and the limit as n goes to infinity. In 3D, it's similar, but you have to switch to volumes and stuff. So in 3D, x bar, y bar, z bar is equal to 1 over the total volume times the sum for all n shapes of xi, yi, zi times the ith volume. Like I said, we're not going to use that 3D version very much. Our problems are going to be mostly 2D problems. And one thing I want you to notice about this is this works with subtracting material too. All you have to do if you want to remove material is treat the area or volume as negative. Okay, so let me go through an example calculation. Let's say we have a shape like this. And let's say this is 1 meter. And this is 1 meter. And the thickness all the way around is 0.1 meters. And we want to calculate the coordinates of the centroid. In order to give coordinates, we have to choose a coordinate system. I'm going to put the origin over here. So that's going to be my coordinate system. And I'm going to do this 2 ways. So the first way is I'm going to break this up into 2 long, slender rectangles. I guess I'll do it like this. So this will be my rectangle 1, this will be my rectangle 2. And the coordinate system is this. Okay, well, rectangles, since we can break this up into rectangles, it's easy to find the centroid of the individual rectangles. That's just the middle along both of the 2 dimensions. So for rectangle 1, the area of that rectangle is, it's a length of 1 meter, a height of 1 meter, a base of 0.1. So the area is 0.1. I'm just using SI units. And the centroid from the origin is 0.05 meters in the positive x. And for y, 0.5. With me on that? And then for the second one, okay, the area is, it's a little different this time because of the way I divided these up. The length, the horizontal length of that rectangle is only 0.9. So the area, all right, this A1, this is A2, is equal to 0.9 times 0.1, so 0.09. And now the centroid, the horizontal centroid, this thing has a length of 0.9, and you have to go from, like horizontally from the origin, you have to go 0.1 in the positive x direction before you get to the left edge of that rectangle. Okay, so it's going to be 0.1 plus 0.45, so this is 0.55. Any questions about that? And then vertically, you have to go up 0.9 to get to the bottom of it, then another 0.05 to get to the middle vertically. So this is 0.95. A total is 0.19. So the centroid of the whole thing is 1 over 0.19 times the area of rectangle 1 times its centroid location, 0.05, 0.5, plus the area of 0.09 times that top rectangle's centroid location, 0.55, 0.95. And your calculators will do calculations like this, just using the multiplication and addition symbols. And what you should get for that is about 0.287, 0.713. One thing you should notice about that is that centroid isn't on material. Okay, so there's no reason that an object centroid has to be at a place where there's material. And that makes perfect sense if you think of a ring, the centroid of a ring is going to be the center of the circle, and there's no material there. And by the way, good like elite high jumpers, when they go over a high bar, they never have their center of mass higher than the bar. So they'll get their whole body entirely over a bar and never once have their center of mass get as high as the bar. That's pretty interesting, I think. Actually, that explains why, how high jump uses the Fosbury flop. It looks funny. You run up and turn around and go over backwards. But that's the reason that's so much more effective than the way people high jump before, because you can get your center of mass so much lower than where your body is, as opposed to the ways they used to do it, where you'd sort of swing one leg over, but you had to get your center of mass up to the height of the bar to get over it. Okay, so that's method one. I'm going to do that same calculation now, but I'm going to do it by thinking of it as like a big outer rectangle and then removing a smaller inner rectangle. Okay, so this time I'm going to start with a big outer rectangle like this. And then I'm going to remove this smaller rectangle. Where this is 0.9, this is 0.9. And we always have to, think about where the coordinate system is. So this is our coordinate system. And then on this one, our coordinate system is going to be over here. You see why I'm doing that? Does that make sense? Any questions? So this is what I'm going to call body one. And then I'm going to remove body two from it. So for body one, rectangle one, the area is 1. The centroid location is just 0.5, 0.5. Rectangle 2, the one we're removing, now this is the one where we're going to think of this as a negative area. So the area of 2 is negative 0.81. And the centroid okay, so from the origin horizontally, you have to go 0.1 meters to get to the left edge of that square. And then you have to go 0.45. So this is 0.55. Vertically, you don't have anything like that. The height is just 0.9, so you just have to go up 0.45. And then the total area is A1 plus A2, which is 0.19 again. I mean, it's the same shape. It has to have the same total area. And so now we can use the formula. So x bar, y bar is equal to 1 over 0.19 times 1 times the vector 0.5, 0.5, and then minus 0.81 times the vector 0.55, 0.45. And if you punch that in, you get the same thing we did before, 0.287, 0.713. Okay, unless a body is non-homogeneous, so different materials at different places, no, is non-homogeneous, the centroid is the center of mass. And so that's where the weight force acts. Okay, so let me do an example where we use the centroid as the center of mass. Bless you. So let's say we have a pin joint at the wall, and it connects to a shape like this. And there's a roller down here supporting it. And let's say this is 1 meter. This is 1 meter. And this is 0.5 meter. And if the mass of this shape is 10 kilograms, what are the reaction loads at the joints? Well, the first thing we have to do is figure out where the centroid is. I guess I'll use a coordinate system.
Wait, does that 1 meter go all the way down to the ground, or does it go to the
Just to the roller.
just to the top of the roller?
Yeah. So I'm going to use a coordinate system here. And I'm going to break it up into these shapes where this is 1 and this is 2. There's my coordinate system. So for body 1, That's a right triangle. The formula for that says, so you have to kind of reconfigure this in your mind. Remember that the formula for a right triangle says that this distance is h over 3, and this distance is b over 3. Okay, but that means that if so the centroid of this shape is like here. Okay, so this formula tells us the distance from here to here and the distance from here to here. Okay. And so it's not in the same orientation, so you can't just blindly plug those formulas in and assume that's your x and y coordinates, you know. The distance we want, because of where I put my coordinate system, is, you know, we want it from the point on the left to this centroid. And so that's going to be 2/3 of the length. So x1, let me do the area first. So the area is 1 times 0.5 divided by 2, so 0.25. The centroid is that horizontal length is 0.5. We want to go 2/3 of that to get from the origin to the centroid. So that's 0.3 repeating. And then from y, we want to go 1/3 of the way from here down to this point. That length is 1. So 1/3 of 1 is also 0.3, but this one's negative because of where I put the origin. And then the rectangle, the area is 1 times 1. The centroid is horizontally, before we get to the left edge of the shape 2, we have to go 0.5 in the positive x direction. So it's 0.5 plus another 0.5 to get to the centroid. So this is 1. And for y, it's negative 0.5. The total area is just the sum of those two, so 1.25. And the centroid of the whole shape is 1 over 1.25 times 0.25 times the centroid of the triangle plus 1 times the centroid of the square (0.86 repeating, negative 0.46 repeating. So somewhere around here. So now that we have that, now it's just a regular statics problem. The pin joint applies an unknown force vector, so I'll call that RA. The weight force acts at the location we just figured out, and that's the mass is 10, so this is 98.1. And then the roller acts here, I'll call that RB. So I'm going to make my about point here at what I call the origin. So the nice thing about that is now that that centroid location that we figured out is the row vector for that weight force. So I'll start with this force RA. The row vector is 0. The force is RAX, RAY. Cross product is 0. Then I'll go to the weight force. The row vector is 0.86 repeating, negative 0.46 repeating. The force is 0, negative 98.1. Cross product is negative 85.02. And then last is the roller, the RB. The row vector where that force is applied is 1.5x, negative 1y. The force is 0 RB. Cross product is 1.5 RB. Newton's second law says RAX, RAY plus 0, negative 98.1 plus 0 RB is equal to zeros. And the moment equation says negative 85.02 plus 1.5 RB is equal to 0. So RB is equal to positive 56.68. And RA is 0 for X, and then for Y, 41.42. And if you change the location of that centroid, you'd get different answers for these, okay? So the answer to this static problem depends on where you locate that weight force.
Could you scroll down?
Yeah. Anybody have any questions about this? Yeah.
For the top part, and you're determining like the triangle where it's 0.5 distance.
Yeah.
How did that become the x 0.33?
Because it's 2/3 away from the origin.
Yeah, so in this so if you're going from the so this distance is b over 3, but if you're going from the point, then that means that it's 2b over 3. And this is h over 3. But if you're going from the point, it's 2h/3. Because they have to add up to a full h or b.
So is 0.5 was one side and 1 meter was the.
Yes, that's right.
Okay.
Yeah, so if you look at the dimensions, it's, yeah. Any other questions? Okay, that's all for today. Sure.
It's like you can hold